topic of pricing electric vehicle charging services with demand charge. And it will be delivered as a pre-recorded presentation, and Zachary Lee would be available to answer questions. Zachary is a graduate fellow at the Research Sustainability Institute of Caltech, California, and a software engineer at PowerFlex Systems. Zach's research interests center on smart electric vehicle charging, where he draws on broad interests at the intersection of data science, computer science, and energy. Without further ado, let's start playing the pre-recorded presentation of Zachary.
My name is Zachary Lee. I'm a PhD student at Caltech. On behalf of my co-authors, I'd like to present to you all our work today on pricing EV charging services with demand charge. And so a bit of background on the problem that we're tackling today. The problem has two parts. The first is the problem of price disaggregation. And if we think about it, as a charging system operator, I have to pay the utility a commercial electricity tariff for the energy that I use. And that tariff usually has two parts: a time of use rate, which is based on when I draw energy from the grid, and a demand charge. And the way the demand charge is calculated is based on your peak usage over an entire billing period, which is typically 1 month. And so you multiply the maximum power draw you drew from the grid in any 15-minute period during that month by a price, which is typically $15 to $20 a kilowatt. And the question we want to answer today is, how can a charging system operator then disaggregate their costs and charge it to individual users based on the demands they place on the charging system? The related question of charging scheduling is also important. So a charging system operator is going to draw power from the grid and needs to decide how to allocate that power to individual users in a way that's fair and that minimizes their cost. And this is the premise of smart EV charging. And so the other question we want to ask is, how can we come up with online algorithms to schedule smart EV charging so that we minimize our costs? And so just to get an idea of what these large-scale charging systems look like, here's a collection of large-scale charging sites at various types of locations where generally dwell time is quite long. So people are going to leave their car there for a long time, and we can then take advantage of that flexibility to schedule them to minimize costs. And so our question is, how should we price this EV charging service in sites like these? Another thing I want to mention is that all of these sites are actually operated by a company called PowerFlex Systems, which spun out of our lab and does large-scale smart charging systems. And so that's kind of the experience we bring to this problem of pricing EV charging services. So if we look at what is the current state of the art in terms of what is being installed and what are people using to charge their cars today, in terms of scheduling, most large-scale EV charging is still unmanaged. And what that means is that as soon as a car plugs in, it's going to charge at its maximum rate. And that requires us to overbuild infrastructure so that we can handle those spikes in demand. Those spikes in demand also lead to really high demand charges. Now, there have been some efforts in industry to mitigate this through simple peak limits. So I might set a limit on the maximum power draw I'm going to let my EV charging system have, and I might use simple scheduling algorithms like first come, first serve, or equal circuit sharing in order to meet those limits. More on the residential side, we also look at delayed charging, where someone might program their EV to not start charging until a low cost period. On the pricing side, a vast number of EV charging systems are still free to the user. But as charging operators are trying to consider how to have a sustainable business model and recoup their costs, we're also looking at flat rates per kilowatt hour or flat rates per minute. But these pricing structures don't incentivize flexibility from the user and don't factor in anything around the utility tariffs that the charging system operator is actually going to have to pay the utility. So if we think about this charging system operator, we should think through what are their motivations. And in particular, we're interested in charging system operators that might be at a workplace or an apartment complex. And they kind of have two main incentives. The first is to keep their users happy. And that means that everyone gets charged the amount of energy they want by their deadline and that prices are kept low. At the same time, they don't want to lose money on this endeavor. And that means they need to minimize their costs and ensure that they have revenue adequacy from whatever pricing scheme they use. So if we look back at the current state of the art, in terms of scheduling, we're not responding to any price signals from the utility, and that means we're paying higher costs. At the same time, we're not providing any incentives or savings to our users, and that means they're paying high prices, and they're not happy about that. So that brings us to our pricing rule. And our pricing rule is really based on three key principles. The first is that we want to prioritize energy delivery, because at the end of the day, we're a charging system provider, and we need to give people the energy they need so they can go where they need to go. But subject to giving them that amount of energy by their deadline, we want to minimize the cost they incur. The second principle that we incorporate into our pricing scheme is the separation of pricing and control. And this is an important aspect of our design because the notion is that as a driver, I don't have control of how the system operator is going to schedule my EV to charge throughout time. What I do have control of is what time I'm going to leave and how much energy I want, and to some extent what time I arrive. So my price should be more based on that, the things I can control, not the things I can't control, which is how the operator chooses to schedule me. At the same time, as the charging system operator, this gives me flexibility on how I choose to do control in real time, because the user is indifferent, because their price is based on a minimum cost schedule and not the actual control signals I send to their car. The final principle is delayed pricing. And this one might seem a little strange, because what it means is that we're not going to charge users until the end of the month, the end of the billing period that the utility gives to our charging system operator. And the reason for this principle is that until the end of that billing period, our charging system operator doesn't know their real costs. They have not realized those costs. And without knowing what those costs are, we can't fairly allocate them to all users. And so what we do is we actually will send a bill to every user at the end of the month. So just briefly, the model we'll use for EV charging, we're going to have N EVs. We'll use a discrete time model where each time interval is roughly 5 minutes long. And for each EV, we can describe it by a tuple. That tuple is made up of an energy request, which is the amount of energy we want to deliver to this vehicle within the time allotted, an arrival and departure time for that vehicle, and a maximum charging rate. And as I mentioned before, we're going to come up with our scheduling based on a minimum cost schedule. And that ensures fairness to the user in terms of how we price them. And so we can phrase that minimum cost schedule or the process of finding it as a convex optimization problem, in particular, a linear program. The objective of this cost minimization problem is to minimize the combination of energy costs and demand charges. We have 4 constraints. The first is that we will meet all of the energy demands for each vehicle by their deadline. The second is that we will respect any infrastructure constraints. And the reason we might have these infrastructure constraints is if we oversubscribe pieces of infrastructure, like say a transformer, so that we can lower our capital costs, then we need to account for the congestion of that bottleneck resource. We also need to charge below the maximum charging rate of the car. And we have this utility variable Q, which is going to represent the peak power draw over the entire billing period. And the horizon of this optimization problem is 1 billing period, so typically 1 month. For our pricing schedule, we're going to use a dual formulation. So we'll assign dual variables to each of these constraints. Alpha will be a session energy cost, which is the marginal price of raising the energy demand of the vehicle. Beta and gamma are congestion prices. And delta is a disaggregation of the demand charge as it's allocated to every time interval. And that leads us to our actual pricing rule. And we'll start with our pricing rule with a time-varying session-specific price. And that session-specific price at every time instance is a factor of 4 components. The energy price, which is based on the time of use price of energy, a congestion price based on how congested the system is at the time, a charger congestion price, and a demand charge component. And because we're using a dual formulation, we can extract many interesting properties about this pricing rule directly from the dual formulation. In particular, we can show that delta disaggregates the demand charge such that the sum over all time of this delta is the same as the demand charge. And the reason this works is that we know by complementary slackness that delta is only greater than 0 if and only if the aggregate current is at its peak at that time instance. So what the user is actually going to pay us now is the product of this price times their optimal charging rate at that time. And that gives us the price the user is actually going to pay for that session, capital Pi. Now, interestingly, we find that this price the user pays is actually equivalent to a session-specific price, not time varying, alpha, which if we remember is the marginal price of the energy constraint. And if we multiply that by the energy delivered to that vehicle, we actually get the same price. So what we can actually charge people is a session-specific price, not this time-varying session-specific price. So it simplifies the pricing rule for the user. At the same time, we can show that if we scheduled according to the cost minimal schedule, this pricing rule is revenue adequate. I mentioned that pricing rule is revenue adequate when we can use the offline optimal schedule, but in reality, we need to schedule online. And that leads us to this online scheduling problem, which we'll use via model predictive control. And what that means is we're going to solve this convex optimization problem at every time interval and apply only the control signals for the first time interval. The duration or the horizon for this optimization problem is roughly 12 hours. And if you compare that to the month-long optimization, we're only looking at a small slice. And so the objective to this, it looks very similar. We have an energy cost. We have a demand charge proxy. And the reason this is a proxy is that we actually have to scale the demand charge so that we account for the fact that our time interval is much shorter. If you're interested in more of how we do that scaling, it's in the paper. We also introduce a non-completion penalty, and the reason we have to do that is we relax our equality constraint on the energy demand to an inequality. And that's important so that we can ensure feasibility in the online setting. We also add this regularizer that encourages us to charge vehicles earlier in their availability period, and that frees up capacity for future arrivals. And we add one additional constraint, which allows us to incorporate previous peaks that have happened in the billing period, as well as to provide an estimate or lower bound of the peak that we can use for our scheduling problem that improves performance. So now we'll move on to some case studies we've run using real data we collected from charging systems at Caltech and the Jet Propulsion Laboratory. So in this first example, we're going to consider offline optimal scheduling. The darker bars for blue and orange are going to be the cost our system incurs. The lighter bars are the actual revenues that we're going to gain from users as they're broken down by the type. And what we can see from this is two things. One, we can see that we're always revenue adequate, which is what we expect. We can also see that the blue and orange bars, both the light and the dark, match exactly. And that's because our pricing scheme perfectly covers both the demand charge and the energy cost of the system. As we move to the online scheduling, you'll notice that the revenue terms haven't changed. That's because of our disassociation of pricing and control. Our pricing model did not change even though we've moved to an online scheduling. You'll see that the other impact of this is that some of our costs are now higher than our revenues. We can't guarantee revenue adequacy because we're scheduling using only limited online information. Despite that, we can see that in general, our revenues are either enough to cover our costs or the shortfall is minimal. We find that in all cases at both Caltech and JPL, the online schedule is within 10% of the offline optimal schedule, which is pretty good considering that we don't have any information about future arrivals. And we have to make decisions about demand charge that cover an entire month using very limited information. Now, I've covered so far the revenues for the operator, but we also might be interested in what are the prices users are paying. And what we'll see from this chart is that most users are paying a fairly low price, but there are a small number of users that need to pay a very high price. And we might ask, why is that the case? And this is a very conscious decision we've made with our pricing rule, which is that users who participate in setting the peak, and thus the demand charge for the month, are going to be responsible for paying that peak. Now, this is very different than existing pricing rules where we socialize demand charge. And in reality, we socialize all pricing variability to all users. In this case, we're going to say, no, you're going to pay for what you caused the system to have to incur in terms of costs. In reality, we might want a more hybrid system where we've socialized some of these costs, but we think this is an important step toward moving in that direction. So in conclusion, we've been able to calculate a session-specific price that's based on marginal costs to the system. We've presented the concept of separation of pricing and control, which helps us to allow users confidence in the pricing rule, despite what the charging operator might choose to control and schedule their vehicle over time. We've shown that our online scheduling algorithm achieves within 10% of the offline optimal using real data from Caltech and JPL. And we've shown that our revenues are enough to cover or nearly cover the cost, even in the online case. I thank you for your time. If you're interested in more work we have around large-scale smart EV charging, or the tools, including this open data set and simulator that we used in this experiment, I encourage you to go to ev.caltech.edu, and I'm happy to take any questions. Thank you.
Thank you very much, Zach, for a very good presentation, very clear. And we do have a question waiting for you in Q&A. And the question is, how can you inform users that it might be a peak time when the bills are only at the end of the month? How actually influence behavior?
Yes, I think that's a great question. And that's why I think I tried to mention in the talk, this is kind of a first step toward a practical algorithm. In reality, one future work that I didn't get to mention in the video because of time is actually trying to predict these prices when users give us their parameters. So within the PowerFlex system that this is based on, users use a mobile app and tell us the amount of energy they want and their departure time. And so right now, this is a very delayed feedback because they're not going to get that bill till the end of the month. But we can imagine training, for example, a machine learning model or some kind of stochastic optimization so that we can provide that in real time to them as they're setting those parameters, and then hopefully influence their behavior so that they provide more flexibility to the system and thus incur a lower cost.
Well, would that answer your question, Brian? Well, I'm sure it has. You have answered the question very well. Thank you very much, Zach. And anything else that you would like to comment about your paper, your line of research? We still have a couple of minutes.
Sure. So I'm happy to say a little bit more. As I mentioned, and as Tungsten mentioned in his work, we do have these open source tools that we're pretty excited about, including that ACN data set that we used in this work and was used in the previous work, as well as an open source simulator. And all the code for this paper is also available on GitHub, and there's a link within the paper to get you there. So, yeah.
Okay. Well, thank you very much. With all that said, I would like to thank all the presenters for the very high quality presentations. The papers are outstanding, and the topic of research is great, and I'm sure it's not going to go away. On the contrary, more and more lines of research will open around electric vehicles. Thank you very much to all of you, and have a great rest of the conference. Thank you very much. Goodbye.
Thank you. Goodbye.
Bye.
Thank you.